So good afternoon, everyone. I hope everyone can hear me fine. So I'm going to show you yet another side of the Pristine survey, focusing on the Milky Way dwarf galaxies, and one particular case, which is the case of the Polytechnique satellites, for which I spectroscopically followed up the outskirts. So first, okay, so if that want to work, yeah. So first, a few words about dwarf galaxies. So these are these very small and faint and very metal poor systems that you find orbiting around Milky Way. And so we had 8 classical dwarfs prior to SDSS, like the very, very big ones. And then we are close to 60 now, so dwarf galaxies and dwarf galaxy candidates, with a very nice picture of Fornax here with the HST. And then why do we care about faint dwarf galaxies? Well, the first reason is that they are very important cosmological probes. So, for example, studying their orbits as shown now, they are orbiting around preferential plane, which is a problem in lambda CDM. There's also, studying their mass and their mass distribution and their mass luminosity, their luminosity distribution, sorry. Can also give you some constraints on the cosmological and hydrodynamical modeling of these systems. And then there's the stellar and galaxy formation and evolution constraints that they can give. They are the building blocks of the halos of massive galaxies. So they are very cool systems to study if you want to kind of understand the very different pathways that stars can take to form elements. But for these talks, I'm going to focus mainly on 2 of these properties listed here. So mainly the kinematics, for which you get the orbit, but also the total mass, like the dynamical mass from the velocity dispersion of the system, and also the metallicity of these satellites. So spectroscopic data are needed to study these satellites. But the problem is that it's a great observational challenge. So this is a great picture that shows you the dwarf galaxy Dynamics 2. So it's quite an extended and bright system already. But then when you want to say, okay, which of these stars are actually members of Dynamics 2, this is what you get. So you see that actually most of the stars that you saw before are actually Milky Way foreground contamination. And so you want to find those stars beforehand as best as possible and then follow them up with spectroscopy. And you need as much stars of dwarf galaxies as possible, because you want as best the constraints you can get on the velocity dispersion and the metallicity of these systems. But as I just told you, the Milky Way foreground contamination is high, and this gets even more critical at the outskirts of this system, which is why most, the vast majority of spectroscopic studies over the years focused on the very inner region of this system. It's because the density is very, very high at the center, and then at the outskirts, because it decreases exponentially, you just have, these stars kind of are drawn into contamination. But the outskirts are important because they kind of carry the information of whether these systems are tidally disrupting or tidally interacting significantly with the Milky Way, which can tell you if you can have biases on the total mass that you're deriving from the velocity dispersion, for example. So we need an efficient pre-selection method, and that's where Pristine comes in. So I'm not going to detail how Pristine works, because I also did a great job of that already. Just to remind you that you can estimate fairly reliably the metallicity of stars only with photometry with Pristine, using this narrowband photometry. And for the galaxies, it's very important because they are overall more metal poor than the Milky Way halo contamination. So just by cutting at arbitrary, depending on the galaxy that you want to study, by cutting on the photometric metallicity and then getting rid of the metal-rich stars, according to Pristine, you can already weed out most of the contamination in a field of view and really be efficient at the telescope to find member stars of those galaxies. And so actually in the Pristine survey, there's a kind of a sub-survey, which is the Pristine dwarf galaxy survey that uses the same filter at the CFHT, but with very deeper data, because these systems are far away, so you need to go as deep as possible, but then the calibration remains the same. So I'm going to show you the example of Bootis 1, which is the latest work that we did, but we also use that method for 3 different systems before. So for Buddhist-1, so here it is, the spatial locations of all the stars in the field of view. So as Nicolas said, the gray does not show very well in the screen, but you have a bunch of stars here, and then the yellow ellipse here is the 2 half-light radii of the system. And the blue circles are the 83 confirmed members in the literature. So it's quite an extensively studied systems for a dwarf galaxy, where you have that many members observed with spectroscopy. But you see that like the vast majority of them are in the very inner region of the satellite. So you have very little information on how the kinematics can change with distance. And so imagine that you want to follow that up with spectroscopy without Pristine and without Gaia. What you really need to do is to look at the main stellar population of Buddhist-1 in the color magnitude diagram, and then kind of select around the RGB of Buddhist-1 and try to go fishing for these stars. And if you do that around the 2 degrees field of view, this is what you get. So these are all the candidates that you would have with a CMD selection without Pristine. Then if you just fold in the Pristine information, so basically discarding all stars, more metal region -1, only with the photometric metallicity from Pristine, you go down to about 83 candidates here. So it's a very, very good way of weeding out the contamination. And then of course you can fold Gaia into that with the proper motions, because the proper motion of Buddhist-1 is well known. And then you can have a very, very effective pre-selection method. So this is what we did. So we followed that system up with the Anglo-Australian telescope, the AET, and this huge field of view, this 2 degrees field of view with the omega spectrograph. And all the red squares that you see here are the new members that we found, which, so we have 27 of them with the AET sample. And then the diamonds here, the kind of transparent diamonds, are the non-members. So don't be alarmed by the fact that there's a lot of non-members. In fact, most of those are actually halo stars that we followed up just because we had fibers to spare. But if we look at the number of stars that were probably Buddhist-1 stars with Pristine Gaia, and that we look at how many of those stars turned out to be members, you actually found a success rate of 75%. So it's really, really good at finding dwarf galaxy stars. And in particular, we found 13 stars that are beyond the 2 half-light radii, so this yellow ellipse. So beyond that, so we more than doubled the number of member stars in the outskirts of the satellite, which is great because now we're going to be able to study the kinematics at greater distances. But before going into the kinematics, you might notice that even though we kind of went fishing in a circle, there's a preferential axis where the members are found, which is more elliptical than what the system is supposed to be when you look at very deep data, again, from the CFHT. And that's something that Fion and Wise found out also last year when they looked at BHV, so blue horizontal branch and blue straggler stars around Buddhist-1. And in the right panel, you see BHVs and blue stragglers, which have more or less the expected magnitudes of Buddhist-1. And you retrieve this extended kind of structure here along the major axis of Buddhist-1. Then, as I told you, we derived the radial velocities for all the new members that we got. So in the blue histogram on the left panel, you have the velocities of the literature, and then in red, the new velocities from the AET sample. And on the right, so let me break it down a bit for you. So on the upper left panel on the right, you have as a function of distance, the systemic velocity of stars in a given bin. So you have a lot of bins, and for each bin, we compute the systemic velocity in the upper panel and the velocity dispersion on the lower panel on the left. And we do that across the major axis of Buddhist-1. And what you can clearly see by eye is that there is a trend in the systemic velocity from one edge of the galaxy to the other. And also some kind of like high velocity dispersion at the edges and a lower one at the center. And if you use the formalism of Martin et Jean 2011, which basically compute the velocity dispersion, the systemic velocity, but also account for a linear gradient, if it exists in the system, you find that there is a radial velocity gradient of 0.4 kilometers per second per arc minute, which is shown here with the probability distribution function on the upper right panel. So you see that it's clearly pointing out toward the non-zero gradient in the system. So it may seem not a lot, 0.4 kilometers per second per arc minutes, but since BuddhistOne has a half-light radius of 10 arc minutes, slightly more than that, it's actually a shift of 4 kilometers per second per half-light radius. So across the system, it's actually quite a huge difference in systemic velocity. And then once you do that, you realize that, of course, since you account for a velocity gradient, the velocity dispersion naturally gets lower because the fact that the systemic velocity changes along the axis will automatically inflate the velocity dispersion if you don't account for it. And that's a problem, of course, if you want to use what most people use in that case to translate the dispersion into a total mass, which is the relation of Wolf 2010. And you can get some huge bias in the resulting dark matter mass and in the mass to light ratio that you measure if you don't account for that. Then we did the exact same thing for the metallicity. So again, you have the literature metallicities in blue and then our sample in red, which is slightly more metal poor. And the same plot again for the metallicity on the right. And this time it's not a linear change in metallicity, of course, over the galaxy, but it's kind of in the ages you have this more metal poor population, and at the center you have a more metal rich one. And so that's something that is like pretty common in classical, very, very bright dwarf galaxies, such as Draco, Fornax, or something like that. But it is only the second time that it's been detected in ultra-bright dwarf galaxy, UFD. So the first one was Tucana 2 by Annie Chitty last year, I guess. And that's the second time that we find such metallicity gradient, in a UFD. And again, you have the PDF of the metallicity gradient on the upper right panel, which clearly, less clearly than before, but still clearly shows that there is a gradient in metallicity. And so just a summary to conclude and have a takeaway message. So first, Pristine is very, very useful for this kind of study, really, really efficient to fish those stars and find those stars, even in the outskirts, that you might not have found should you not have this metallicity information. And when you combine it with Gaia, it's really, really good at doing the trick. And so for the BuddhistOne analysis in particular, we found 27 new members, and especially 13 in the outskirts, so almost tripling the number of stars in the outskirts of the system. So the system seems to be slightly more elongated than what we thought before. And that's confirmed by the BHV's and Bruce Stragler's study that I showed you. And then if you combine like this very, very elongated shape with a systemic velocity gradient that really truly exists in the system of 0.4 kilometers per second per minute, and also this metallicity gradient, the kind of takeaway message that you have from all of that is the fact that BuddhistOne is probably significantly tightly interacting with the Milky Way, and that it's maybe have been even more massive before. So it's not clear whether it had lost like a lot of mass, but it's clear that for this system in particular, it's you have to take that into account if you want to properly model the mass of the system, and in particular the dark matter mass. And that's kind of a cautious warning and a cautious flag as well, that it might be the case for other systems, and that it's probably worth doing that kind of thing for other systems and check whether the mass that we have for all the dwarf galaxies that we know are not maybe biased by 20, 30, 40%, depending on how the tidal interaction goes. But still, it can be very, very impacting on the mass that we understand for dwarf galaxies. So thank you for your attention. If you have any question, please feel free to ask.
Thank you. Thank you for your talk. I have a naive questions. So if you include the gradients in the analysis, of course, as you explained, the dispersion gets lower. But why stop at the gradient? Is there something special dynamically that you have to take into account the gradients and not higher polynomial modes, which would get your then the dispersion even lower?
Well, I mean, it's possible that we haven't dug that much into that. I guess one of the reasons is that, I mean, it looks pretty kind of linear when you look at the bins. although polynomial might work. It's something that we haven't checked. It's kind of our analysis stop as, be careful, and there's a gradient there. But as long as we're not trying really to properly model the dark matter mass or the dark matter profile and those kind of things, we don't want to push things too much.
Okay, thank you.